I'm going to chair the first session of today, and it's my pleasure to introduce our first speaker, Joaquim Serra, from ETH Zurich, who's going to speak on stable phase transitions, open questions, and new results. So Joaquim Serra did his PhD 10 years ago at the Polytechnic University in Barcelona, and then after a brief intermezzo, I believe, in a big data company, he moved for a postdoc to Berlin, and then to ETH, where he did a postdoc with Alessio Figali, and where he is now a professor, and received numerous prizes, among which I just mentioned the MS Prize 2020 and an ERC starting grant, which is still active at the moment, and we're looking forward to your presentation.
Okay. Thanks a lot for the introduction, and thank you so much for the invitation. It's really a pleasure to be here. And today I'm very excited because it's the first time I will speak about a project in which I've been working for the last years, and we'll see how it goes, but I'm excited to present these new results on stable phase transitions. But I will start giving a bit of motivation. I will start very basic with the motivation of what we want to do here. I hope you can read. The screen is a bit small, so in any case, I will read everything. So due to forces similar to surface tension, we know that some physical phenomena display these interfaces that tend to minimize the surface area, at least when you see on macroscopic scales, right? But while the mathematical model that is surface area, right, is scaling invariant. This means that when you rescale, when you multiply your surface by a factor r, then the area is rescaled like r squared at every scale, right? The actual physical energies are, of course, not scaling invariant. For instance, the quintessential example of area minimizing surface that would be in physics, a soap film. If you go to a very small scale of size comparable to a molecule of soap that is about 5 nanometer, of course, this is not, it doesn't make any sense to say that the scale is comparable to this scale. The thing looks like a surface. It's a 3D thing, right, when you zoom in enough. So you see something more of this type of structure. So yet, we know, the mathematicians know that the regularity, so the absolute energy minimizing configurations behave like minimal surfaces at macroscopic scales. And this we know because there's a regularity theory for energy minimizing minimal surfaces. If you want, the regularity theory for energy minimizing minimal surfaces has been extended to several important scale-dependent models, right? And a notable instance is this macroscopic regularity theory of Ovidio Sabin for Allen-Cahn, that I will describe what is the Allen-Cahn equation. And this was about 15 years ago. This was a breakthrough on this macroscopic regularity theory for models that look like minimal surfaces, but only at large enough scales, let's say. A key consequence of this, mathematical consequence, is that absolute minimizing configurations for this scale-dependent model really behave, we can prove they behave like area minimizing surfaces when we look at macroscopic scales. However, what happens if we replace this absolute minimizing hypothesis by, and we want to consider like local minimizers, so stable equilibria. So stable equilibria are defined as configurations that minimize the energy among sufficiently small perturbations. And if you want, they encompass the observable states in nature, because as you know, if something is unstable, it will decay towards a more stable state, right? And as we will see, these efforts to establish a regularity theory similar to that of minimizing minimal surfaces for stable equilibria in these scale-dependent models, this has some mathematical challenges, right? And I will talk about this. And then, given this, it's arguably premature to say confidently, at least for a mathematician, that all stable configurations in those models will resemble minimal surfaces at macroscopic scales. So we expect this to be true, but we have no conclusive proof of it. So this is not something important, because many times we're used in mathematics that you do the ideal model, and then a perturbation of the model is just, you give to a PhD student or someone, and you add a parameter, right? But here we are talking about a model where we understand the ideal model very well, and when you perturb, it's not a perturbation, really. So there is a deep difficulty when you add the scale-dependent model, and that's why I will describe a bit more. So the thing is that we would like to do the regularity theory for stable critical points, and this is the main question, I would say, in the calculus of variations. Now, let me describe very easily a cartoon almost, but what is phase transition and phase field models. So phase transition, in the simplest scenario, I would think of sort of two states that coexist in a spatial region, right? The two states could be ice and water. It could be two fluids, right? That immiscible fluids that tend to separate. Or it could be two bacteria that don't like each other. So there are many models that lead to this kind of, and mathematically, I would be considering a sort of black and white picture. And the thing is that we have, between the black and the white, there is an interface, and somehow in the models that we consider, this interface increases the system's energy, and this prompts the minimization of the surface area of the interface, right? So now, the phase field models, so there are many, right? But in the simplest case, that everything is scalar, so there is no vectorial models or complex number, no. So this would be like what would be the scalar case of the Ginzburg-Landau, if you want. So you want to describe the phase transition, and instead of using a black and white model, a black and white model would be a function from the space Rn, taking values either +1 or -1, black or white, right? And then what you do is you replace it by a smoothed model, because you want to describe things by solutions to the PD. You like the PD, right? And then this smoothed model, instead of seeing a sharp transition, a sharp interface, you will see a smoothed interface, and the transition will happen like this. It will happen from value -0.99 to value +0.99 in a very small region, in a very steep interface. And this is the role of this parameter epsilon that we'll see. The models will have a parameter epsilon, and this epsilon has unit of length, is the width of the interface. This is the moral of the story. Now I will be more precise on which model. This is just an illustration for a lava lamp, how you should imagine. So there are two fluids that are separated, and then, but there is a region in which the fluids are a bit mixed, right? But this very tiny region. So Allen-Cahn, if you want, is a pragmatic phenomenological model, one of these phase field models, but it enjoys a notable popularity in physics, calculus of variations, even geometric analysis. There have been important theoretical results proved using this Allen-Cahn. And the Allen-Cahn model is this one here. You consider an energy that is the sum of two pieces. The first piece is just the Dirichlet energy, the same for harmonic function, grad u squared, but you put epsilon in front, so you are not penalizing too much gradients. You're counting the gradients, but with small penalization, because the epsilon is multiplying. And instead you have a second piece here, 1 over epsilon W of u, and this W is this double well potential with wells at -1 and 1. So this penalization forces sort of functions that try to minimize these or try to be a local minimizer or something will tend to be very close to -1 and +1 most of the time, right? And then what you expect is, at least for minimizers, you can justify this very well. In equilibria, you expect the transitions will occur on fat surfaces with thickness epsilon, as we saw. And in one dimension, you can so you can compute the Euler-Lagrange equation associated to this. You get an ODE, and you can even compute the explicit solution, and it does what you expect, right? It goes from -0.99 to +0.99 with epsilon, essentially. Okay, so what is the connection between this model like Allen-Cahn? There are other families, right? But the most famous in this context maybe would be this one, the Ginzburg-Landau or Allen-Cahn. So the connection between these and minimal surfaces is given by this classical theorem of Modic and Mortola from the 70s that says that if you have a sequence of minimizers of the Allen-Cahn with parameter going to 0, then this converges to the characteristic function of a set. The function u goes to a function that is either +1 or -1. Right? And the jump set, where it jumps from +1 to -1, is really a minimizer of, so the set is a minimizer of the perimeter, so the boundary of the set, that is the jump set, is a minimal surface. So you are really converging, and they even have a gamma convergence that is a bit more sophisticated. But the idea is that here, when epsilon goes to 0 from a situation where you there should be 3 lines here, sorry. So you have 3 level sets like this, 0, -0.9, and 0.9. They converge to one single level set. Again, here the picture is wrong, unfortunately. So you need to imagine the 3 level sets like are almost parallel here. I don't know, they disappeared. And this sort of gamma conversion result, this sort of weak convergence or strong in L1, but this can be improved. Actually, this follows from Sabin combined with recent results of Wang and Wei. So if you have a sequence of minimizers, then at least in low dimensions, the 0 level sets are smooth hypersurfaces with uniform C2 alpha bounds, right? And they converge to minimal surfaces smoothly, and the mean curvature converges to 0, and you can quantify the convergence. So remember that for a minimal surface, the mean curvature, the sum of the principal curvatures at any point of the surface is 0, right? And you can prove this in terms of epsilon for these models. Let's say the mean curvature is a power of epsilon that goes to 0 when epsilon goes to 0. But of course, this is for me. So the picture is very clear for minimizers, right? But for this Allen-Cahn is a non-convex functional and like functions of one real variable. For a non-convex functional, you can have absolute minimizers, but you can have also local minimizers or other critical points, finite Morse index, whatever. And of course, all the critical points, so a subset of them is a stable critical point, so that are these local minimizers, and then the minimizers are just even a smaller subset, right? And this is the stable critical point, as we said before, is very relevant because it's the points that you can see, that you can see when you build, so when you do a minimal surface with soap in your house, right? Well, I don't know, I have children and I do this. So you can see that some surfaces stay, some surfaces disappear. Like in the catenoid, if you separate the two circles enough, then you see this, it kind of degenerates because the catenoid it's mathematically unstable, and you see this, that the mean curvature flow makes it collapse, right? So then the question is, so if these stable if these stable configurations are the ones that are very important in physics, so what can we say? So can we extend this regularity theory for Allen-Cahn to stable critical points, at least in 3 spatial dimensions, because it's the physical 3 dimensions at least. And so this is hard, as we'll see. The first thing that I want to point out is that there is a connection between this question and a celebrated conjecture of De Giorgi on modern solutions of Allen-Cahn that says that is still open in full generality in dimensions 4 to 8. And the connection is that if you can do this, if you can establish the regularity theory for stable critical points in n dimensions, then this implies that the De Giorgi conjecture in 1 dimension more, n+1. This is a known argument, right? So, and since the De Giorgi conjecture is open, in particular, this is stronger. So it, of course, is open, and several people tried, right? But And let me also mention that this is kind of related to a question in minimal surfaces, that this is a stable Bernstein type result, where you where you have a surface that is a hypersurface, a minimal hypersurface, and you know it's stable inside of the ball of radius 2, right? Let's say it's embedded, so it's as nice as you want. Qualitatively, C-infinity embedded everything, but you only know that it's stable inside of the ball of radius 2, and then you want to show in low dimensions that the second fundamental form of the surface is universally bounded. So there is a quantitative bound on the second fundamental form. This is equivalent to this is known to be equivalent, to a Bernstein type result, that is this question: must any complete stable minimal hypersurface in Rn be a hyperplane? Right, this is a Bernstein type, but for stable. And this is known to be true. This is classical in dimension 3, when the ambient dimension in R3 and you have a two-dimensional surface, is known to be not true in dimension n equal 8 or higher. And now there have been, in the last year, recent breakthrough in dimension 4 and 5 using methods from positive Ricci curvature. So these are, but all of this is all these methods is positive Ricci curvature are very restricted to the geometric setup. So they really use the structure of minimal surfaces. They do not allow for a perturbation. So you put the epsilon, you are lost. So not even this that is fairly sophisticated, just this result that is very smart, but it fits in half of a page of proof. Even this result, you put it to Allen-Cahn, you don't know how to do anything, right? So that's why Allen-Cahn, you cannot say it's just a perturbation, at least for when you deal with the stable. Now, let me describe what is known. So what is known about the stable critical points. Let me see. I'm going quick. Let me describe a bit what is known about stable critical points and what could be the open questions. I already said, but let me give more specific open questions. So as I said, a natural question now is if we can generalize this robust convergence of Allen-Cahn to the minimal surfaces to the case of stable critical points, at least in 3D, and partial results. We have some partial results in this direction, but very few. So let me describe all of them. So the first thing is from 2000, is Ambrosio Cabré. What they showed is that they showed the classification of entire solutions for epsilon equal 1, and there's some energy growth assumption. So they consider, remember that the classification of entire solution, did I say this, or is maybe, yeah, okay, it's not, I will say it after. So I will say it after. Actually, well, I will explain this here, 1 second, sorry. So this is about solutions for epsilon equal 1, but in super large domains, right? Which is the same as actually the whole space. And getting epsilon equal 1 and super large ball is the same as ball of radius 1 and epsilon small, because remember that epsilon is just a length. So you can make the length 1 just zooming in, right? But they assume that you are in the entire R3. In the entire R3, you have a stable solution for E1, the energy for epsilon equal 1. And this extra assumption that, that let me tell you, is not innocent at all. I mean, it's reasonable, but not innocent, is that the integral of the energy in a ball is bounded by a constant R squared for any ball, very large balls, right? Then they show that there exists some direction in the sphere such that the U is one-dimensional, so it depends only on the variable E, scalar product X, right? So the level sets of U, all the level sets are hyperplanes, right? Use of this one-dimensional form. It's like the one-dimensional solution, but you put it in some direction. Now, so applying this classification result recently, Wang and Wei and Chodos and Mantolidis can deduce a very precise theory, a very precise regularity theory for solutions, stable solutions in a ball of radius 2 in R3. Now, it's U epsilon, so it's a stable solution for the epsilon Allen-Cahn with the parameter epsilon. And you need to think that the epsilon is going to 0. So you're interested in what happens as epsilon goes to 0. And the assumption they put, that again is not innocent, is that the energy of U epsilon, of U, but is U epsilon, is bounded by a constant that is independently of epsilon. It's like the energy bounds are independent of epsilon. When this happens, then you have a super precise regularity theory. And it's optimal, sort of, this regularity theory. So this, what they prove, you can really construct solutions that do that, right? Which is very interesting because you will see why the problem is hard here when you switch to stable. So they show that the zero-level sets, there could be many. So the zero-level sets will satisfy some curvature estimate, right? Also, the mean curvature will converge to 0. So the zero-level sets will be almost minimal surfaces. But then there can be many zero-level sets, and well, as many as C, essentially. There could be as many as C. And they could be very close to each other. So they could be the distance, and this is optimal, is about square root of 2 epsilon log epsilon plus O of epsilon, right? So this is a separation, and they sort of interact, the zero-level sets very weakly, but they interact. And this is hard to prove. I mean, this is a regularity theory that to take into account these interactions and show these and these at the same time, is one of, is a very, very good result, I would say. Now, so similar to minimal surfaces, and so the question, so this sort of theory extends, this sort of theory in one way that they did in a later paper, extends also to up to dimension 7, but only if you know this kind of results. So if you know the classification, so all the question now boils down, all the question to have the regularity theory boils down to this classification problem. So is every stable critical point from Rn to plus and minus 1 of this energy, the Allen-Cahn energy with epsilon equal 1, of the form 1D function, is a 1D function, phi of E dot x for some E in the sphere. Again, this is only true, is now up to dimension 7, because for 8 or larger there are counterexamples, known since some years ago. And the only result we know of in this direction, but not assuming the area bounds. Remember that this result was with area bounds, with this assumption that for all R this is bounded the energy. So if you don't want to assume area bounds, the only result we have by now, as far as I'm concerned, is for a related model. So results for a model that is that looks like minimal surfaces at larger scales, I mean, and of this type of phase. So is this result for the so-called Piles-Navarro energy that when you put Laplacian to the 1/4, whatever, square. This is a different energy, a different Fourier symbol, but it has the same qualitative properties, and then it's a bit more non-local, but that still the limit for this energy as epsilon goes to 0 is the minimal surfaces, right? But today I would like to describe something more similar to Allen-Cahn. So let me just gather here the two sort of two open questions. So the general open questions are already said, but here I would like to identify two open questions that look more sort of feasible in the next few years. So the first question would be to classify stable critical points, so the stable de Giorgi or stable critical points in the R3, right? So to say that they are of this form, and then you can classify them. But without energy growth assumption, removing the energy growth assumption. Now, I mean, this is hard. People tried, but, well, this is hard, right? But doesn't look impossible now. This looks, so this in higher dimensions probably is a bit easier than this, because it's like to show the stable de Giorgi for Allen-Cahn with energy growth assumptions in dimension 4 to 7. So here we want to assume the energy growth, like the energy in a ball of radius r is like r to the n minus 1. That is the sort of the energy when the function looks like this. But we want to go to higher dimensions. This, I believe, should be easier than this, but comparable. No, maybe. No, maybe it's still easier, but still is not known how to do it. And many consequences, when you do this, there are many consequences that follow also. Like for instance, you can do, this has application in all this theory of min-max minimal surfaces. You can construct min-max minimal surfaces that are smooth up to dimension 7 and things like that. Okay, so let me just mention that the minimal hypersurface analog of question B is something that is known since many years, is classical. So complete minimal surface under this sort of area growth assumption are classified by these, the main works from dimension 4 to 8 is Schoen-Simon, Yau, and Schoen-Simon, right? But again, the strategy from these minimal surfaces cannot be transported to the Allen-Cahn. So there is no perturbation theory here that works. But today I'm going to simplify my life a little bit, and then I'm going to talk about the free boundary, what we call the free boundary version of Allen-Cahn. This, as far as you know, was introduced for the first time in a PhD thesis of Kamburov with David Jerison at MIT, right? And the idea is very reasonable. So you here remember that the energy of Allen-Cahn, or when you have a double well potential, what you want to do is to penalize the intermediate states between -1 and 1, right? And here, what they did is to consider a potential that is just the characteristic function of the open set -1, 1, right? So if you are between -1 and 1, you pay 1, and if you are either -1 or +1, you pay 0, right? So as I told you before, so the solutions for the Allen-Cahn model look like this when you introduce the parameter epsilon, right? They look like very steep transitions, but still smooth transitions. The solution for this modified model is just -1, then it goes up super quickly like a line in 1D with slope 1 over epsilon, and then it goes, or 2 over epsilon, and then it goes like +1, right? So it's this is of course in 1D. In higher dimensions it's a bit more complicated. So what happens in higher dimensions is that yeah, you have this, right? You have it's a free boundary problem. The function U will be exactly -1 in some regions. There is one free boundary. There is a second free boundary, and between the two free boundaries, the Laplacian is 0, because you see the potential is constant. So when you compute the Euler-Lagrange equation, you just get harmonic function, right? And the effect of the nonlinearity, the effect of the nonlinear stuff is giving a free boundary condition. It says that the normal derivative of U is like 2 over epsilon, right? And this should approximate, in some sense, these two free boundaries should look, at least if epsilon goes to 0 and you consider minimizing configuration or something, they should look like minimal surfaces. Right? You see the qualitative behavior is the same, right? It's not, from the big perspective, there is no difference between these two models, right? And still, this model is epsilon dependent, so it's scaling dependent. It has many of the difficulties that this model has, right? And now, so in a recent work, so it's not yet out, but it will be in the next few months, I would say. So this is what I wanted to describe a bit, some ideas from the proof. But let me give the theorem first. You can guess is every stable critical point u from R3 to -1, 1 of this energy with the characteristic function, so of the free boundary Allen-Cahn, must be 1D symmetric, right? So this is the analog of the conjecture for Allen-Cahn, but for this particular potential. That is good because it retains many of the difficulties, but it's less technically, so as we will see, there are less technically involved things. Still, well, this is a proof that is more than 70 pages, but so it's still, there are technical points, but for Allen-Cahn they can be even worse. So if the corollary would be that if you have a solution u epsilon, a critical point u epsilon, a stable critical point of the same energy but now with an epsilon in the ball of radius 2, then in the ball of radius 1, the second fundamental form of the zero-level set or of any of the two free boundaries is bounded independently of epsilon, right? And the mean curvature is very close to 0 as a power of epsilon. I'm not being more precise. So I hope that the picture is clear. So here would be the zero-level set and the two free boundaries. You need to imagine that the function is like +1 here, identically +1, then there is a free boundary. It goes from +1 to -1, then -1, and then +1 here. So and in every of these small region, there is a transition. And the function is just harmonic inside these very small regions, right? So now let me give, just in 10 minutes, a rough idea of how the proof works. It's very rough, right? Because I cannot give many details, but it's impossible to give so many details. But the idea is that if you have, this is a very general thing that is well known since many years, that if you have a stable critical point of some functional like this, or even more general, so you can consider what is called second inner variations, second variation, but when you perturb, you do domain variations, right? You compose with diffeomorphisms, and you compute the second derivative with respect to the times of your variation. And then you get a condition. You get a condition that this is the Sternberg-Sundrum condition, that in this case, right, it's like this, is the integral in the, so remember the region for the, at least for the epsilon, right? The region where u is less than 1, where the absolute value of u is less than 1, is the tiny region between the two free boundaries. And everything, so for the rest, the solution is just +1 and -1. So everything interesting happens in this region, right? And if you integrate in this region the Hessian square of your function, this is bounded by constant over R square, the sort of the volume of this interface, the volume that is like the area, right? And this is C over R squared. This is just from the scaling. This is a Hessian, so this scales like C over R squared. This is very similar, very analog to the stability inequality for area minimizing minimal surfaces. And this is the piece of information one needs to use to conclude the flatness. And now the idea that is very simple is, okay, let me, so this tells me that at least for R large, this left-hand side will be small in many regions, right? Because I'm dividing by R squared. So let me consider a cube grid. This is a bit a cartoon, but you can guess the sort of modification one needs. So let me consider a grid of size 100 times 100. Here I'm not doing epsilon. Epsilon is 1, right? So this thing is 1. Is morally 1. And then I'm taking a grid 100 times 100. And then I'm saying I said that the cube of this grid is good, and I will paint it green. A cube intersecting the free boundaries, right, is good. If this left-hand side is less than eta 0, where eta 0 is some small dimensionless parameter, let's say. And it is bad instead if it is bigger than eta 0. Now the thing is that bad cubes, you cannot do much about them, but at least you can count them, because each bad cube will contribute something non-trivial to the left-hand side of the stability inequality. This is a very simple idea. I'm not discovering. And then the idea, more than this, would be, okay, if we can show that in some sense, in the good cubes, the surface, at least in the good cubes, because here there is no hope, the surface really look like and behave like true minimal surfaces. So they are really a perturbation of minimal surfaces. Hopefully, maybe you can use the proof or a modification of the proof of Pogorelov or whatever, the proof of the area bounds for minimal surfaces, taking into account these bad cubes as errors in some sense, and then you can make it work, right? So we are trying to go back to the perturbative, even if we know it's not a perturbation in some sense. So what can happen inside the good cube? So what could go wrong in this strategy, right? Because the first time you think of this strategy, you think, okay, in the good cube, this integral of the Hessian square is very tiny, so it will look everything like mostly flat, because the Hessian square equal to 0 is just flat, right? So it should look more or less flat. So we expect to have some transitions +1, -1, and in between, some regions where harmonic functions that look like planes, maybe very steep planes, but sort of planes. Ideally, the different components of this free boundary with this free boundary should not interact, and then I can treat each of them separately, right? So the free boundary problem for this one and this one they don't see each other, at least for this free boundary. The problem is that a priori a possible scenario is that two of these transitions came close to each other, and then a neck between them is created. So this is a 2D picture because I don't know how to draw, but you need to imagine that these are like a plane, another plane, fat plane. It's a fat plane, and they are connected, they are sort of separated and connected with a neck, like this. So the region U less than 1 is connected, right, through the neck. So these are illustration of the neck. These I found in the internet, and then I asked ChatGPT to produce a neck, and it did these nice pictures. So I wanted to credit ChatGPT for this, because this will be in my next slide, right? So now, using the picture of ChatGPT, the thing is that when you zoom in, so if you want to understand how bad or how these necks could look like, so let me mention something. The energy in 2D, this is each neck contributes to the left-hand side of the stability inequality. In 2D, it's critical. So each neck contributes like a unit of energy. So in 2D, you would not have too many necks. But when you are in 3D, a neck of size delta contributes delta to the left-hand side of the stability. So it's worse than minimal surface, because a neck in a minimal surface also gives you a quant of energy, sort of a quant of second fundamental form. At least it's a dimensionless. Here is not dimensionless. Here the energy is not an energy. It's this thing, right? This integral on the left-hand side for a neck, it has unit of length to the power 1. So if I do a tiny neck, I don't see it at the level of energy. And that's why I need to zoom in and go to a completely different regime. So if you have a microscopic neck and you start to zoom in, you end up with this problem. It's a different free boundary problem related. It's the so-called Alcafarelli problem. So let's say that we are zooming in around -1, right? So we just do U of rho x -1 divided by rho, and we send rho to 0, and to see a neck that is microscopic, we see now of size 1. And this problem is a harmonic function here. The V is 0 here, and the normal derivative of V is +1 here in the inner direction. Now, the thing is that if you just look at the PDE, solutions to this PDE exist. So it's not that you could, even in 2D, you can produce, there are explicit solutions to this PDE. And it not only exists, but they are finite index, so they have finite Morse index. This means that just looking at the stability inequality is not easy to rule them out, right? Because it's very borderline. When you have solutions to the PDE that are finite index, it means that they are energetically as close as they can be to be stable. You need to use something else, some regularity at infinity or something more sophisticated than just brutal energy comparison, right? And in 3D, as I said, it's even worse because it's easy to conceive like two planar-like free boundaries joined by multiple necks with sizes going to 0, and each neck contributes nothing to the left-hand side of the stability, right? So ruling this out in 3D is hard. At least it was hard for me, and this occupied us for some years now. But now we could finally do it in a joint work with, so it's a very Swiss, well, none of us is Swiss, but we are all working in Switzerland, right? Hardy-Chan in Basel, Fernandez Real, who is in Lausanne, and Figali and myself, we are in Zurich. So we can prove that the stable solutions of the Alcafarelli in 3D must have flat free boundaries, and this is the theorem. So if you have now V from R3 to 0 plus infinity is a stable critical point of this functional, you see this is the Alcafarelli, then it must be of either form. You can have like, you can be a half plane solution, or you can be two half plane solution with a parallel free boundaries and nothing else. So this rules out sort of any configuration of necks, right? Any sort of configuration of necks in 3D. And this is actually one of the main, the hardest part, or one of the hardest parts to show the other theorem, right? So it's one of the I mean, this was, this kind of result was used, so there were papers using this conjecture to prove a regularity theory for this problem. There is a paper of Jerison and Kamburov that assuming this, they obtained some consequences, so it was around. But our main motivation for this problem was also to solve the other problem for the free boundary Allen-Cahn, because we really need this. Without this, you cannot do anything, because these necks completely ruin your argument when because then the different phases start to interact, and even in good cubes, in these good cubes where these one, the green ones, even in these good cubes, if you could have necks, they look nothing like really the free boundaries looks nothing like a minimal surface, essentially. So then you are in big trouble, let's say. So a corollary of this, to finish, is like if you have a solution, a critical point, the ball of radius 2 of the Alcafarelli, then it satisfies dimensional curvature estimates in the ball of radius 1. This is very simple, that's why, so you have a stable solution in B2. Here you have V equals 0, then V positive, then the picture will really look like this. In sort of half of the ball you are 0, then half of the ball you are positive. And the second fundamental form of the free boundary in between, this is two-dimensional surface, right? The second fundamental form, the principal curvatures are bounded by a constant that is a dimensional constant. And I think with this, I thank you for your attention. I'm finished.
Thank you very much for your presentation. So are there any questions, remarks, comments? Okay, then I'll start off. So I have one technical but simple question and another more conceptual one. The technical one is, say you consider stable stable critical points of in Rn, of Rn. What's the metric that you use for the perturbation, or in what sense is that stable on Rn?
You mean because it's non so stable.
What kind of perturbations?
Yes. So the thing is that you use compact perturbations. Always.
Compact perturbations.
Yes.
Is there a simple explanation why say, an approximation of a mean zero surface, but which is not flat, why that does not lead to stable critical points?
An approximation to a mean zero surface. So could you repeat the question?
So take a saddle surface, extend
Yes.
it, so an infinite saddle surface.
Yes.
Why is that not stable?
Um,
On a compact
so the
perturbations?
saddle surface, you cannot make it infinite.
Ah, okay, that's the point.
The thing
Good.
is
Yeah, good. Okay, thanks. And so the more conceptual one is you have oriented surfaces because you use Allen-Cahn and you have two phases.
Yes.
What changes conceptually if you go to, say,
Yeah, I'm happy with the two phase. I mean,
yeah.
so I'm happy with assuming. So this kind of, I mean, it's even 3D, right? We are. I'm happy with assuming everything embedded, two-sided, everything we want, right? So, so when they do, actually, when they did in the so the in the geometric, so these Schodoshman and people, right? They started to try to prove it for two-sided and embedded and everything. And actually, I think that the proof, a posteriori, the proof doesn't need it, right? So when you prove, they know how to. But I think that the conjectures, you can assume everything you want, because, but of course one needs to see a posteriori if the proofs could go well without the two-sided. Or for us, it's very natural that it's two-sided. And in any case, even this application, this has application in min-max construction and things like this. And very often, when you do min-max, when you do things like this, a surface that is one-sided is always, you can approximate by a sort of double cover of two-sided. And really the regularity theory is like when you look at the level of the approximating objects like Allen-Cahn, so it's two-sided, but you are telling, in the limit you are saying something about one-sided surfaces as well, right?
Okay, okay.
A more applied question. One may also take the point of view that when we are having natural phenomena, we are in metastable states, which just take a long time. So you have very nice techniques. Do you think you can say something about these states either by transforming the model into an approximate model where you still can discuss about stable states, or if not, can you also say something about metastable states in this technical setting?
So metastable would be, I guess, sort of stable for the gradient flow for in time, right? Something like. I mean, if you, the thing is that I'm not discussing here subtle. So I would say, if you have even you can assume. I don't think it helps in anything. You can assume that you are a strict stable critical point, and then as far as I know, this should be a sort of attractor of the dynamic, right? Because then it's a well, the energy has a well that you cannot escape, and you are going to this well. So you can even assume that, I don't think it helps in any way. You can assume that this is unique or something like that, doesn't have any degeneracy. And still, the a priori estimates for the curvature, of course, if you start to quantify your assumption, that you are minimized locally in a sort of neighborhood, then you can do other things, but then it's a bit cheating. But if you really want something that is stable in time, I would say that is sort of the same question or the same difficulty. Yeah.
Okay, before we thank our speaker once more, let me just recall that now we have a coffee break and we reconvene here in this lecture hall at 11:15 again. Okay, thank you once more.
Okay.